Welcome to the Crazy Hat Chemist. So another video here on solubility. So let's get moving. Bam! So today we are talking about the solubility product constant, i.e. the KSP. All right, yeah! So a precipitation reaction is always written in the following way. Okay, we got our calcium phosphate, that is Ca3 parentheses PO4 with a parentheses and a 2. Notice that this is on the reactant side and it is a solid, i.e. a precipitate, a solid. Okay, this is in the form of a cation and an anion. The cation is written first, of course, the anion is written second. This is a solid. Okay, and then we have some equilibrium arrows because this is an equilibrium reaction. Okay, an equilibrium reaction that is, of course, reactant favored, as noted in the size of the arrows, i.e. the larger length arrow is towards the reactant side. Okay, and then we have our products. We got 3 calcium ions, that's aqueous, plus 2 phosphate ions, that's also aqueous. This is balanced for charge and for mass. Okay, this first one here is the cation, and it is written in the solution form because we are always having ions in solution on the product side for a KSP reaction. This is the anion. You could have written the anion first and then the cation second. It doesn't really matter. Okay, a precipitation reaction, of course, follows the solubility rules, and you can look those up or follow one of my videos, and are deemed as insoluble precipitates or compounds. Okay, that dissociate, that is break apart to a very small extent. This is why they are all reactant favored. Okay, so we're going to write the equilibrium constant expression for this reaction of calcium phosphate. So KEQ is equal to products over reactants with the stoichiometric coefficients as exponents. And notice I did include the solid here, but recall that solids, of course, are not included in any K expression of any kind. Therefore, what we're going to have to do is we're going to have to cross this out, because solids are not included in KSP or K expressions of any kind. So now what we're going to do is we're going to rewrite this K expression, this KEQ, and we're going to rename it. Okay, and we're going to call it a KSP, and it is the products over the reactants with the stoichiometric coefficients of exponents, but of course solids, liquids are not included, and the reactant is always a solid when it's a KSP. Okay, this KSP is now called the solubility product constant. It's not the equilibrium constant product here, but it's the solubility product constant. Notice that there's never a denominator on these terms here, because that denominator is a solid, and that's what you start off with on the reactant side. Okay, all right, so let's keep on going. We got more to do here. Okay, a generic precipitation reaction can then, of course, be written as the following. And here it is. We got AX, B, Y. That's a solid. I got my equilibrium arrows. Notice that my equilibrium arrows are towards the reactant side. We got X, A, Y plus, that's aqueous, plus YB, X minus, aqueous. Notice that on the reactant side, it is a solid, that is certain. On the product side, you have a cation and you have an anion. Okay, all right. So that reactant is a cation-anion combination combined so that the charge ratio is 0, and it is, of course, a solid if you are dealing with a KSP. All of these reactions are reactant favored, and you're soon going to find out looking at the K value itself. We have the cation and we have the anion. They are both in solution, that is aqueous. Okay, all right. So we're going to write the solubility product constant for this reaction here that we have right here as a generic reaction, and this will be applied to all of them that we can be doing here. Okay, so KSP is equal to, and we have brackets, and those brackets mean molarity concentration. Okay, so in that first set of brackets, we have A, Y plus, that tells you what the charge on the cation of the A is. It's in aqueous, and it's to the X power because that was the stoichiometric coefficient. Then B in the brackets to the X minus, that is the anion, and that's also aqueous, to the power of Y, which is the stoichiometric coefficient for the B. Okay, notice that there's no denominator here because the reactant is always a solid. Okay, so the reactant is always a solid, so there is no denominator. Okay, and of course solids are not included in any kind of K expressions, but certainly not KSPs. Okay, since all precipitation reactions are reactant favored, we're going to see that equilibrium arrow, notice that yet one more time again, then the value of the KSP is going to always be less than 1. Okay, so recall from the previous video, when the KEQ is less than 1, it is reactant favored, and the equilibrium lies towards the reactants. Okay, these are insoluble precipitates in dealing with this unit here of KSP. Since they are insoluble precipitates, then they are generally viewed as insoluble, but to a very small extent they break apart to form their ions. We are interested in the concentration of ions in solution. Okay, so a precipitation reaction and their associated solubility product constants can be found in a reference book. So maybe in the appendix of your textbook or in the handbook of chemistry and physics. That's the CRC. Okay, so here's an example of silver chloride. So chlorides, bromides, and iodides are soluble except for silver, mercurous, and plumbous chloride, bromide, and iodide. So this is an insoluble precipitate. Well, notice that equilibrium arrow lies to the left towards the reactant side, so it is reactant favored. The products are going to take the cation and the anion, break them apart with their associated charges in aqueous solution. Okay, we're going to write the KSP value for this, or the KSP expression. That's products over reactants with the stoichiometric coefficients as exponents. Solids are not included, and we have that silver ion and the chloride ion. They both have two stoichiometric coefficients as 1, so therefore their exponents are 1s. We can look this value up inside that reference textbook in the appendix of your textbook, if you will. And as 1.6 times 10 to the negative 10, notice that this is times 10 to the negative 10, so it is certainly reactant favored because that value is less than 1, so it's reactant favored. Here's another one, and that is cuprous iodide. Okay, this is also a solid, and it forms its ions that slightly dissociate to a very small extent of copper 1 and iodide ion. And the KSP here equation is copper ion times the iodide ion. Stoichiometric coefficients as 1s, therefore the exponents are as 1s. And you can look this value up, of course, in your textbook as well. That's 5.1 times 10 to the negative 12. Again, times 10 to the negative 12 is also indicating that this is reactant favored. Here's another one. This is plumbous chloride. Okay, plumbous chloride, we have plumbous ion and chloride ion. Notice that this time the ratio is not 1 to 1 like on the two previous ones, but it's actually a 1 to 2 ratio. That is 1 lead, that is the plumbous 2 plus charge, and 2 chloride ions. So now if we write our KSP expression for this one, we're going to have the lead to the first power, the chloride to the power of 2, second power. Okay, and you can look this value up in the appendix as well, and that's 2.4 times 10 to the negative 4. Notice that this equilibrium lies again to the reactant side because the exponent is negative. Here's another one. Calcium fluoride is an insoluble precipitate as well. It forms calcium 2 plus ions and 2 fluoride ions. I have the KSP expression for this. Products over reactants, stoichiometric coefficients as exponents, as solids are not included. Okay, the calcium ion times the fluoride ion to the power of 2, that is squared. And that is 4.0 times 10 to the negative 11. That's also reactant favored. Okay, here's another one, bismuth 3 sulfide. Okay, bismuth 3 sulfide is an insoluble precipitate, and it forms the ions of 2 bismuth 3 plus ion and a 3 sulfide 2 minus ion. I'm going to write the KSP for this one as well. Remember, the reactant, that's the solid, is not included, but the exponents are going to be very important here. So the bismuth 3 plus ion to the power of 2, and the sulfide ion to the power of 3. That's cubed, right? And this is 1.6 times 10 to the negative 72. That times 10 to the negative 72 is a negative value. That's a reactant favored, of course. Okay, and then we have calcium phosphate. I included this one in the introductory lecture here. We're going to break this apart. We got 3 calcium ions and 2 phosphate ions. And I'm going to write the KSP expression for this. It's calcium ion to the exponent of a 3, that's cubed, and the phosphate ion to the exponent of 2, that's squared. And you can look this up, and that's 1.2 times 10 to the negative 26. Okay. Notice that all these KSP values have negative exponents and are therefore less than 1 and therefore are very reactant favored. That's why when you follow the solubility rules, then these are all insoluble compounds. But in this unit, we're going to find out that they are not completely insoluble and there is an equilibrium and there are ions, that is cations and anions, that do go into solution. We are most interested in the concentration of those ions that go into solution. A little break here. Don't forget to donate to my website. Get a sticker. Gotta love it. All right. Sweet. Bam! So we're going to keep on going. Direct comparison of the solubility of two salts on the basis of their KSP values can only be made with salts having the same ion ratio. So we've got the same ones that we had here before, and I'm going to highlight the silver chloride and the cuprous iodide. They are both in a 1-to-1 ratio, so therefore we can compare their solubilities. Okay, and I've noted this right here. So the silver chloride and the cuprous iodide are in the same 1-to-1 mole ratio of cation and anion, and they can be directly compared with their KSP values. And you should see that times 10 to the negative 10 for the silver chloride and times 10 to the negative 12 for the cuprous iodide. That means that the cuprous iodide is more insoluble. It is more reactant favored. And the silver chloride is more product favored and it is more soluble of the two. Okay, I'm going to give another comparison, and that is the plumbous chloride and the calcium fluoride here. And the calcium fluoride and the plumbous chloride are both in a 1-to-2 mole ratio. Therefore, the KSP values can also be directly compared here. You should see that I have a times 10 to the negative 4 for the plumbous chloride and a times 10 to the negative 11 for the calcium fluoride. And of course, calcium fluoride is more reactant favored. It is more insoluble, and plumbous chloride is more product favored and it is more soluble. By the way, all of these are insoluble. They're all reactant favored, but of the two, which one is more insoluble? Calcium fluoride. Which one is more soluble? Plumbous chloride. And going back to that original introductory lesson here, and that is you can selectively precipitate out certain ions by looking at their solubilities. Okay, you should see that this cuprous iodide and the plumbous chloride, well, these two are different mole ratios. So since these ion of the cation and the anion ratios are not in the same 1-to-1 or 1-to-2 ratio, you cannot directly compare their KSPs and figure out which one is more soluble or insoluble. You actually have to solve for the concentration of the ions in solution to compare them. Okay? All right, I am the Crazy Hat Chemist, and of course, I gotta get a hat. And this one here is a helmet. And one of my favorite pastimes is, of course, riding my bicycle. I encourage all of you to ride your bicycle. Of course, with a helmet, it's critical. Okay, donate to my website, get a cool t-shirt. Look at that. Awesome. If you like that video, give me a thumbs up, subscribe to my YouTube channel, and I'm going to see you next time for more solubility rules. Bye for now.